Okay, so today we're going to be talking about circular motion, and this is going to be motion of an object that rotates around a single axis. Now, a good way to look at this is the lab that we did yesterday, and now the axis that it was rotating about, if I can untangle this, is going to be this axis right here, which was our PVC pipe. So here we have something that's rotating, and you can see it here if I did it horizontally, it's rotating around a single axis. So we have circular motion, you can see the circle right there, and this is going to be an object that rotates around a single axis. Another example is going to be a tire wheel. So I have a tire wheel right here, and this is the single axis right through the center, and it's going to be an object that's rotating around. Okay, so we can talk about a wheel. We can be talking about a wheel on a car. This could be a Ferris wheel. This could also be a roller coaster. Although the wheel isn't moving, what happens if the roller coaster now is moving around this circle? Or a Ferris wheel that you have, the wheel itself is moving like this. So we're going to be talking about all sorts of motion that is around a circular path with one axis or one center. Okay, we're also going to be talking about a special type, which is uniform circular motion. The uniform is the key word, and uniform just means that it's going to be at a constant speed. So we're not going to be speeding up or slowing down as we're going around this circle. So if we're riding a roller coaster, the speed of the roller coaster car around that circle is going to be even. It's not going to get faster or slower. Okay, so it's an object that moves around an axis at constant speed. Well, we're going to be talking about that speed that it moves around the circle. So the important thing here is we call it tangential velocity. The reason why it's called tangential velocity, if you recall from the lab yesterday, if I were to spin this and I were to let it go, all of a sudden, say I wasn't holding it around and I spun it around and all of a sudden let it go, which is the direction that this rubber stopper would fly off? Well, the direction that it would fly off would be a tangential. And the key word tangential. Now, tangential comes from the word tangent. And tangent comes from something that touches in only one spot and it's perpendicular. So this velocity right here of the object right here, if we were to cut the string, it would fly off in that direction. At this point right here, if all of a sudden I were to cut the string, it would fly off in this direction. So you can see that it's perpendicular to the circle and perfectly straight and only touches in one spot. This is what we call our tangential velocity, and we use the little sub t to tell us that it's a tangential velocity. This tangential velocity is dependent upon the radius of the circular path. So yesterday when we did our lab, the radius was the distance from the stopper to the center here. If that radius increased or decreased, that is what changed the velocity. So this is our tangential velocity. If I increased it, I have to spin it faster to keep it going. And so you can see that the radius of the circular path is what's going to be important to keep that velocity or that tangential velocity constant. Okay, so now tangential velocity back from kinematics is just a change in distance over the change in time. So the distance that we're going to be talking about is the distance that the object moves from here to here. Now, one full rotation is the circumference of the circle. So later on we're going to talk about this, but this is just S, it's just the arc length that that object has moved. Okay, well, we talked about tangential velocity, but now what about acceleration? So we said that uniform acceleration is constant speed, which means that that acceleration would have to be 0 if the tangential velocity is constant. But we do have acceleration when we go around a circular path. Well, how do we get that? Well, we have to remember that velocity is a vector, and a velocity has a magnitude and a direction. Okay, so we're saying right here that if it's constant speed, then this magnitude doesn't change. But in this case, you can see here that the direction of the velocity has changed. At the first time, it's going in this direction, Over here, it's going in that direction. So we have a change in direction of the velocity. And this change in direction is what we're going to be talking about. It's the acceleration based on the change in direction of the velocity, not based on the change in the magnitude. So we're going to talk about the change in direction over a change in time. Well, this is a special type of acceleration. So how do we find out what the change of direction is? Well, remember when we find out the change of velocity, it's just change in velocity is just our final velocity minus our initial velocity. Well, how do we do that? Well, this is just tip to tail method. So we're going to say V2 plus a negative V1, okay, which is really V2 minus V1. And what we're going to do is we're going to do tip to tail. Now, a negative V1 is just the V1 and you flip direction. So if V2 looks like this, and negative V1 is just the same as V1 but flipped, now we're going to do tip to tail. So we're going to start with V2, and then what we're going to do is we're going to do a V1. So here's V2, and then V1. And then what we're going to find here is this is going to be our change in velocity, which is our V2 minus V1. So we know that from here to here we have an acceleration that's pointing in this direction. Excuse me, the direction would be right here. You can see here. Okay, and we're going to talk about, this is the acceleration that we're going to be talking about. The change in velocity is the acceleration that we're talking about. Well, it's a special type of acceleration, and it only happens when you're going around a curved pathway, because if you're going straight, you don't have the change in direction. This is what we call centripetal acceleration. The word centripetal is a Greek word that comes from center seeking. So what's happening here is going to be an acceleration that looks towards the center seeking. Okay, so it's always going to be pointing towards the center of the circle. So first let's talk about the magnitude, because acceleration is a vector. It has a magnitude and a direction. Well, the magnitude comes from this equation. The acceleration centripetal, and we use that little c telling us it's centripetal, just like we use the acceleration in the x direction or the acceleration in the y. Well, now we have an acceleration in the center direction. This equation is going to be the tangential velocity squared over the radius. And we know that from the lab that we did yesterday, because the acceleration changed when we changed the radius, and the acceleration changed when we changed the speed, and we talked about that in the synopsis that we wrote. Well, the direction of this is always towards the center of a circular path. So let's talk about a Ferris wheel, okay? And you're at the top right here in this bucket of the Ferris wheel, and you're hanging down, okay? And the Ferris wheel is going to be turning this way. Well, you have a tangential velocity that's going straight at this point. Well, the acceleration is always towards the center of the circle. Well, now what happens when you're down here? Okay, so you're still on your Ferris wheel, but now you're at the bottom. Well, if you look here, now we're going to be moving here. Your tangential velocity is going that way because this is going around in a circle. Well, your acceleration is always towards the center. So now our centripetal acceleration will point upward. Okay, and we'll get in more detail later on. The units that we use for acceleration are the same as any other acceleration, meters per second squared. Okay, so remember the magnitude is the tangential velocity squared over the radius. The direction is always towards the center of that pathway, and the units are meters per second squared. So let's try a problem that uses centripetal acceleration. Okay, so we're first going to be talking about a washing machine tub. So a cylindrical tub of a washing machine has a radius of 34 centimeters. During the spin cycle, the walls of the cylinder rotate with a tangential speed of 5.5 meters per second. Calculate the centripetal acceleration of the clothes spinning against the tub. So we're going to be talking about if this was a top-loading washer. Okay, here's the tub, and you have something, and this is going to spin around really, really fast, and what happens is the clothes spread out to the outside radius of that tub, and what we're finding is what is the acceleration. Well, we know from here that it has a radius of 34 centimeters, but we need to be in meters, so we're going to convert that 34 centimeters to 0.34 meters. We also know that it has a speed, a tangential speed of 5.5, and we're looking for centripetal acceleration. So we're going to start with our equation. Our centripetal acceleration is our tangential velocity squared over the radius. We just plug the numbers in. Don't forget to square it. And then we're going to divide it by that, and we end up with the centripetal acceleration of 89 meters per second squared. And remember, the direction is always towards the center. Okay, let's try another one now. Okay, a test car is moving at a constant speed around a circular track. If the car is 48.2 meters from the track center and has a centripetal acceleration of 8.05 meters per second squared, what is the tangential speed? Well, we're going to start here. We know that it has a radius of 48.2 meters from the track center, and the centripetal acceleration is 8.05 meters per second squared. What is the car's tangential speed? Okay, so we're going to use our equation. Centripetal acceleration is v tangential squared over r. Then what we're going to do is we're solving for v tangential. So we're going to cross multiply. Centripetal acceleration times r is vt squared, but we don't want it squared. We want to solve for just vt, so we take the square root of both sides. Plug in our equations, 8.05 times 48.2, and then take the square root of it, and we end up with 19.7 meters per second, and that is the tangential velocity. Okay, so what we're talking about here is a car moving down a circular track. An example that you can see here is if you're driving on I-95, okay, so here's I-95, and you're going to exit at, I think Fisk Boulevard is a good example, but Fisk Boulevard, the exit takes you around a circle. Okay, so if you're exiting here, you have a circular path with a radius r. Well, what happens? There's always a sign right there, and that sign tells you to slow your speed down. The reason why is because your centripetal acceleration, even if you're at a constant speed, is going to make you feel like you're going much faster. And you guys know what I'm talking about. As you exit that highway, if you don't step on the brake, you're going to end up going so fast, you'll end up going straight this way. So to be able to keep along that path, you have to slow the velocity down. Another way that you could do it is increase the radius. So if this radius were large enough, that curve, you wouldn't have to slow the velocity down. But there's two factors that affect the acceleration. One is the velocity, the other is that radius that you're going to be turning.